The universe is not what you were taught, not even close. The number you heard in school, whatever it was wrong in a way that is hard to overstate. Tonight you will see the boundary of what light can reach and what lies beyond it. 2 trillion galaxies inside just the portion we can observe. A total universe that may have no edge at all, no boundary, no end, just more. The size of what you are about to encounter is not the kind of large that is simply impressive. It is the kind of large that breaks the tools you would normally use to think about large things. Numbers stop working, analogies collapse, the usual mental scaffolding gives out. What replaces it is something closer to vertigo. Here is what astronomers know, and what most people were never told. The universe has a visible edge, but that edge is not a wall. It is a horizon, a limit of information. Beyond it, space continues. We simply cannot see it because light from those regions has not had time to reach us yet. And the distance to that horizon is not what a simple calculation would give you. Space was expanding while the light was traveling. The source that sent the oldest light we can detect is now roughly 46 billion light-years away, not 13.8 billion, not even close. That gap alone should stop you cold. And then there is the question of what lies beyond even that. Whether the universe goes on forever, whether the laws of physics themselves could have come out differently somewhere else, whether this is the only universe there is. These are not philosophical questions. They are scientific ones, with evidence attached. We begin with the most basic question you can ask, and the answer that ruins everything. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Light travels at 186,000 miles per second, and that number sounds fast until you start using it as a ruler. To make sense of it, start close. The moon sits roughly 239,000 miles from Earth. At the speed of light, that distance takes about 1.3 seconds. If you could flip a light switch and somehow aim the beam at the moon, it would arrive before you finished the motion. That feels fast. That feels like instant. Hold that feeling, because it is about to become useless. The sun is 93 million miles away. Light takes 8 minutes to cross that gap. Right now, the sunlight hitting your window, warming the floor, casting shadows across the room. That light left the sun 8 minutes ago. You are not seeing the sun as it is. You are seeing it as it was at the moment you poured your morning coffee. The sun could, in principle, do something dramatic this very second, and you would not find out for another 8 minutes. That delay is small enough to ignore in everyday life. At larger distances, it becomes the whole problem. Keep going outward. The nearest star to our solar system is a dim red dwarf called Proxima Centauri, sitting 4.2 light-years away. That is not 4.2 years of travel at the speed of a rocket, or a plane, or anything humans have ever built. It is 4.2 years of travel at 186,000 miles per second, the fastest speed that physics permits anything to move. In miles, that works out to roughly 25 trillion. There is no vehicle, no shortcut, no workaround. The light arriving from Proxima Centauri tonight left that star 4.2 years ago. Whatever is happening there right now, you cannot know it. The information is still in transit. This is where the concept of a light year starts to reveal what it actually is. Most people hear the word and assume it is a unit of time. It is not. It is a unit of distance. 1 light year is the distance light travels in 1 year, which works out to about 5.88 trillion miles. But here is the thing that matters. Every light year of distance corresponds exactly to 1 year of delay. You cannot separate the two. Distance and time are locked together at the speed of light, and this is not a quirk of language. It is a physical reality built into the structure of the universe. The further something is, the older the image you receive from it. Distance does not just mean far, it means old. Stretch the scale further. The center of the Milky Way sits about 26,000 light years from Earth. The light arriving from that region of the galaxy tonight departed when human civilization did not yet exist. When that light began its journey, the last ice age was still underway. Humans were painting cave walls and hunting with stone tools. The stars at the galactic center have had 26,000 years to change, to move, to explode, to die since that light left them. What you see when you look toward the galactic core is a portrait of the past, 26,000 years out of date, and there is no way to update it faster than the speed of light allows. The Milky Way itself spans roughly 100,000 light years from edge to edge. This means that if something happened at one edge of the galaxy right now, the other side would not know about it for 100,000 years. The galaxy is not a single synchronized object in any meaningful sense. It is a collection of regions, each receiving information about the others on a delay determined purely by distance. The supernova on the far side of the Milky Way is invisible to us until its light arrives. It could already have happened. The light is already on its way. We simply have not received the letter yet. Outside the Milky Way, the numbers leave familiar territory entirely. The Andromeda Galaxy, the nearest large galaxy to our own, lies 2.5 million light years away. The light-reaching telescopes from Andromeda tonight departed 2.5 million years ago, when the species that would eventually become humans was still emerging in Africa. Andromeda is a different galaxy, containing hundreds of billions of stars, and yet the most current image we have of it is over 2 million years old. Everything we know about Andromeda is history. Push the distance to hundreds of millions of light years, and the delay grows proportionally. Push it to billions, and you are looking at the universe when it was young, when galaxies were still forming, still colliding, still sorting themselves into the structures we recognize today. The light arriving from the most distant objects ever observed left its source when the universe itself was less than 1 billion years old. Those objects have had over 12 billion years to evolve since then. Whatever they are now, the image we have of them is more ancient than almost anything we can conceive. This is the core of the light year problem, and it is not a problem of mathematics. It is a problem of perception. When you look at the night sky, the experience feels immediate. You open your eyes, the stars are there, the light arrives in real time. But none of it is real time. Every photon entering your eye has been traveling. The nearby stars you see without a telescope are showing you light that left them years or decades ago. The faint smudge of the Andromeda Galaxy, just barely visible on a dark night, is an image from before humanity existed. The sky is not a window. It is a museum, and every object in it is an exhibit from a different era. The universe does not have a single present moment that you can see all at once. What you see is a layered collection of past states, each one further back in time, the further away the object sits. The concept of cosmic distance cannot be separated from the concept of cosmic delay. And once you understand that, the question of what the universe actually looks like right now, not as it was, but as it is, becomes one of the strangest questions you can ask. The further out you look, the older the image, and that distinction is going to matter a great deal. The observable universe is not the universe. This is the first thing to get clear, because the confusion runs deep and it matters. When astronomers talk about the observable universe, they are talking about a specific sphere, centered on Earth, bounded by a specific distance, inside which light has had enough time to reach us since the Big Bang. Outside that sphere, there is more space, more matter, more everything. We simply cannot see it yet, and in some cases we may never be able to. Think about standing in a field on a foggy night. You can see perhaps 100 meters in every direction. Beyond that, the fog swallows everything. But you know the field does not end at the fog. The ground keeps going. The grass keeps growing. There is more world out there just past the boundary of what your eyes can reach. The cosmic horizon works the same way. It is not a wall. It is not a physical edge where space stops and something else begins. It is a limit of information, the furthest distance from which light has had enough time, travelling at 186,000 miles per second, to reach us across 13.8 billion years of cosmic history. Beyond it, the universe continues. We just cannot receive its signal. This principle applies universally to all observers. What we see is constrained not by the edges of reality, but by the speed of light itself and the finite age of the cosmos. Any photon traveling through space operates under these same constraints. The boundary we observe marks the limit of our cosmic neighborhood, not the edge of existence. It is a deeply humbling realization that the entire starry sky visible to our telescopes represents only a fraction of what actually exists beyond our reach. This distinction matters because people regularly conflate two separate things. The observable universe is a function of time and the speed of light. The universe itself is something larger and, as best we can tell, far stranger in its extent. Conflating the two is like reading the first chapter of a book and assuming that is all the book there is. Now here is where the numbers get genuinely strange. If the universe is 13.8 billion years old, and light travels at a fixed speed, the most distant light we can receive should have spent 13.8 billion years traveling toward us. So the edge of the observable universe should sit 13.8 billion light years away. That is the calculation most people run. It is also wrong. The actual radius of the observable universe is about 46.5 billion light years. The full diameter is roughly 93 billion light years. That number is not a typo. It is not an error in the research. It is what you get when you account for the fact that space itself has been expanding the entire time the light was traveling. Here is the picture. When the most ancient light in the observable universe began its journey, it left a region of space that was extremely close to us by cosmic standards. The universe was far younger and far smaller. That light set off toward us, and it has been travelling ever since. But the space it was travelling through was not standing still. Space was stretching. The region of space where that light originated was being carried further away from us by expansion, even as the light moved in our direction. The light kept making forward progress. It kept closing the gap, but the gap itself was growing. By the time the light finally arrives, the source, the original region that emitted it, is no longer anywhere near where it started. It has been carried outward by billions of years of continuous expansion. Today, that source region sits roughly 46 billion light-years away. Even though the light it sent us only needed 13.8 billion years to arrive. This is not a trick. It is not a paradox. It is simply what happens when the medium that light is traveling through is itself in motion. Space does not carry light along with it. Light still moves through space at the same fixed speed, but space carries everything else, including the origin points of that light, further and further out. The result is an observable universe far larger than a naive calculation would produce. This expansion continues even today at an accelerating rate, driven by something cosmologists call dark energy, a mysterious force permeating all of space that pushes matter apart and stretches the very fabric of reality itself. Some people find this unsatisfying. If the light took 13.8 billion years to arrive, how can the source be 46 billion light years away? But there is no contradiction here. The source was close when the light left. It is far now. Both things are true at different moments in time. The distance to the source today reflects where it has ended up after billions of years of expansion, not where it was when the signal departed. What all of this produces is a specific shape. The observable universe is a sphere, and Earth sits at its center. Not because Earth is special, not because we occupy some privileged location, but because the cosmic horizon is defined entirely by our line of sight. It is centered on us the way any circle of visibility is centered on the observer standing inside it. An astronomer on a planet in the Andromeda galaxy would be sitting at the center of their own observable sphere, different from ours, overlapping with ours, but centered on them. An observer on the far edge of what we can see would look out in every direction and see their own bubble of space, their own 46.5 billion light-year radius, much of which we cannot access at all. No one is at the center of the universe. The center is everywhere, because every point in space is the center of its own observable bubble. This is one of the harder conceptual shifts in cosmology, and it is worth holding for a moment. There is no throne at the middle of everything. There is no preferred vantage point. There is just space, and every location in it surrounded by its own sphere of accessible information, all of those spheres overlapping in the vast connected fabric of the cosmos. The 93 billion light-year figure, the full diameter of our observable universe, represents the product of two things: the age of the universe and the expansion of space over that time. Remove the expansion and the number shrinks to something close to 27 billion light-years. Add expansion back in, run the actual mathematics of how space has stretched over 13.8 billion years, and you arrive at 93 billion. The expansion is not a correction or a footnote. It is the dominant factor. It is what makes the observable universe so much larger than instinct predicts. And this is still only the observable universe. This is still only the foggy field within our circle of vision. The field itself, the actual universe beyond the horizon, may dwarf this sphere by factors that have no easy expression in plain language. The 93 billion light-year figure is just the part we can see, and that distinction is the whole point. In December of 1995, Astronomers pointed the Hubble Space Telescope at a blank patch of sky and left it there for 10 days. The target was chosen carefully, not because it was interesting, because it appeared to contain almost nothing. No bright stars cluttering the frame, no nearby galaxies washing out the exposure, no known source of light to interfere. Just a small, dark square of sky in the constellation Ursa Major, selected specifically for its emptiness. The patch was tiny. If you held a dime at arm's length and then walked it 75 feet away from you, that coin would cover more sky than what Hubble was staring at. This was not a grand panorama. It was a pinhole. And for 10 consecutive days between December 18th and December 28th, the telescope accumulated light from it. 342 separate exposures stacked and combined into a single image. When the image came back, astronomers did not know what to do with it. That blank square was not empty. It was covered, packed from edge to edge with galaxies, approximately 3,000 of them, resolved from what had appeared to be nothing. Spirals, ellipticals, irregular blobs of light at various stages of development, scattered across the frame at different distances, different ages, different sizes. Each one was not a star. Each one was an entire galaxy, an island of hundreds of billions of stars, so far away that without Hubble's extended stare, it had been invisible, buried in the dark. Some of the faintest were so remote that their light had been travelling toward us since before our solar system existed, and there were 3,000 of them. In a pinhole, the implications were almost too large to process quickly. If a patch of sky that small, one of the most unremarkable patches anyone could have selected, contained 3,000 galaxies, then what did that say about the rest of the sky? The math was straightforward and alarming. If you took that tiny field and tiled it across the full sphere of the observable sky, scaling the galaxy count across the entire celestial surface, the numbers climbed into the hundreds of billions. Not hundreds of billions of stars, hundreds of billions of galaxies, each one containing hundreds of billions of stars. At the time, the working estimate in astronomy was somewhere around 200 billion galaxies in the observable universe. That figure had not been measured directly. It had been inferred, modelled, extrapolated. It was the best available number, and most researchers accepted it as roughly correct. The Hubble Deep Field did not immediately overturn it, but it put pressure on it. Here was a direct count from a single, deliberately empty slice of sky, and the raw numbers were already pushing toward the high end of every estimate on the table. What had seemed like a reasonable figure began to look like a lower bound. Robert Williams was the director of the Space Telescope Science Institute at the time. He made the call to point Hubble at that empty patch. It was not a risk-free decision. Hubble was a shared instrument with enormous demand. Giving 10 days of its time to a blank region of sky with no guaranteed payoff required defending the choice to a community of researchers who had their own targets waiting. Williams used his director's discretionary time, a block of observing hours reserved for his own judgment. He pointed the telescope at nothing, and he waited. When the image came back, the scientific response was immediate. Within weeks of the data being released publicly, hundreds of papers had been submitted, attempting to analyze what was in the frame. That release was itself deliberate. The team made the Hubble Deep Field data available to the entire scientific community almost immediately, rather than holding it for exclusive use. The reasoning was straightforward. An image this significant deserved the full weight of the field applied to it. What followed was one of the most concentrated bursts of analysis in modern observational astronomy. Researchers measured galaxy sizes, shapes, colors, and redshifts. They traced the evolution of galaxy types from the early universe to the present. They found evidence that galaxies in the distant past were smaller and more numerous than the large, well-formed structures visible nearby. The image was not just a count, it was a chronicle. The obvious next question was whether that single field was representative. Were astronomers lucky or unlucky? Had they accidentally pointed at an unusually dense region or an unusually sparse one? Follow-up observations answered this fairly quickly. A southern hemisphere counterpart, the Hubble Deep Field South, was observed in 1998, targeting a completely different region of sky. It produced a nearly identical result. The universe, at the level of depth Hubble was probing, looked statistically the same in every direction. The original deep field was not a fluke, it was a fair sample. The implication held. Then, in 2004, astronomers pushed further. The Hubble Ultra Deep Field used the newly installed advanced camera for surveys, a more sensitive instrument than what had been available in 1995. The exposure time was longer, roughly 1 million seconds of accumulated light over several months of observation. The field of view was similar in size. The result was nearly 10,000 galaxies, more than 3 times the count from the original deep field, in a comparable patch of sky. Some of the galaxies in the ultra-deep field were among the most distant objects ever observed, so far away that their light had left them when the universe was less than 1 billion years old. The telescope was not just looking across space, it was looking back toward the beginning. In 2012, the process went one step further. By combining a decade's worth of exposures taken over the same central region, astronomers produced the Hubble E-Extreme Deep Field, the deepest image of the universe ever made by that point. Around 5,500 galaxies in a patch of sky smaller than the original deep field. Some of them barely resolved, some of them visible only because they had been photographed hundreds of times and the signal had been pulled painstakingly from the noise. Every time the depth increased, the galaxy count increased with it. There was no point at which the universe thinned out, ran dry, or showed signs of an edge. The deeper they looked, the more there was, and that pattern has not reversed. For a long time, 200 billion was the number that appeared in textbooks. 200 billion galaxies in the observable universe. It was a staggering figure. Astronomers arrived at it by taking what Hubble had revealed in its deep field images and scaling outward across the whole sky. The maths seemed solid. The number seemed final. For decades it sat in textbooks and documentaries and science museum placards without serious challenge. Then, in 2016, a team of researchers at the University of Nottingham looked at the same data everyone else had been using and concluded that nearly everything astronomers thought they knew about galaxy counts was wrong. The team was led by Christopher Consellis, and what they published was not a minor revision. It was a tenfold increase. The actual number of galaxies in the observable universe, they argued, was closer to 2 trillion, not 200 billion. 2 trillion. The difference between those two numbers is 10 times. 10 times more galaxies than every major textbook on the planet had printed. The reaction from the scientific community was not immediate dismissal. The methodology was serious, and the logic behind it was difficult to argue with. Here is the core of what Consellis' team figured out. When Hubble stares into the deep field and counts galaxies, it is only counting the galaxies it can actually see. That sounds obvious, but the implication runs deeper than it first appears. In the early universe, galaxies were smaller, much smaller. They were dim, compact, irregular clumps of stars that formed in the first few billion years after the Big Bang. These ancient, faint structures were below the detection threshold of any telescope we have ever built, including Hubble. They were simply too dim to show up. What happens to small galaxies over billions of years? They merge. They collide, pull each other apart, combine and reform as larger structures. The big galaxies we observe today are the products of countless smaller mergers stretching back across cosmic time. Consolice's team worked backward through that process. If these are the galaxies we see now, how many smaller galaxies had to merge to produce them? When they ran the numbers, the count ballooned. Most of the galaxies that have ever existed are gone, consumed by mergers, absorbed into the larger structures we can observe today. They are not missing. They are inside the galaxies we already counted. But they were once distinct galaxies, and when you add them back into the total, the number climbs steeply. 2 trillion. Most of them extinct. Most of them invisible to any instrument humanity has constructed. The observable universe is full of ghost galaxies that left no direct image behind. What does 2 trillion actually mean? The human brain has no natural capacity for numbers at this scale. It accepts them without absorbing them. The way you accept a number like the distance to the sun. You nod, you move on, and you have understood nothing. So try this instead. Take a single grain of sand, not a large grain, an ordinary one, the kind that sticks to your foot at a beach. That grain represents 1 galaxy. Now imagine filling a container with enough grains to reach 2 trillion. You would need roughly 6,600 full bathtubs of sand to hold that number of grains. That is 2 trillion grains of sand. And each grain is a galaxy. Each galaxy is an island of stars. On average, hundreds of billions of them. Some galaxies hold 1 trillion stars. Some hold more. The Milky Way, our own galaxy, contains somewhere between 100 and 400 billion stars, and it is not considered unusually large. The star count that comes out of this is a number that language is not really equipped to handle. Astronomers estimate the observable universe contains something in the range of 1 septillion stars. That is a 1 followed by 24 zeros. If you counted 1 star per second without stopping, you would need longer than the current age of the universe to finish. By a factor of billions. The number does not shrink when you sit with it. It just stays there, refusing to fit inside anything a human mind can hold. Consolice's result raised another question immediately. If most galaxies in the early universe were too faint for Hubble to detect, what will the next generation of telescopes find? The James Webb Space Telescope, launched in late 2021, was designed in part to answer exactly this. Its infrared sensitivity allows it to peer into the earliest epochs of galaxy formation in ways Hubble cannot. Already, Webb has returned images of galaxies from the universe's first few 100 million years. Galaxies that look nothing like what standard models predicted. Galaxies that are larger and more structured than they should be at that age. The count is not closed. Every time the technology improves, the universe produces more. There is something almost aggressive about this pattern. Astronomers point a better instrument at the sky, expecting to refine the previous answer, and instead find that the previous answer was dramatically short. The universe does not reward assumptions of completeness. Every boundary that has ever been drawn around the galaxy count has eventually been pushed outward. 2 trillion may itself be a lower bound. And yet, even accepting 2 trillion as the working figure, there is a fact about it that tends to get lost in the counting. Every single one of those 2 trillion galaxies sits inside the observable universe. Not the universe, the observable universe. That distinction matters more than any single number in this conversation. The observable universe is defined not by the actual edge of space, but by the limit of what light has had time to reach us since the Big Bang. It is a sphere centered on Earth, or more precisely, on wherever the observer happens to be, with a radius of about 46.5 billion light-years. Beyond that radius, there is more space, possibly much more, possibly infinite more. The 2 trillion galaxies are the contents of our bubble. They are the local inventory. Whatever lies beyond the cosmic horizon is not included in that count because we have no way to count it. And all of that, every last one of those 2 trillion, is the part of the universe we happen to be able to see. In 1929, Edwin Hubble noticed something strange about the light coming from distant galaxies. It was shifted towards the red end of the spectrum, and the further the galaxy, the bigger the shift. This was not a small anomaly. It was not instrument noise or a calibration error. Every distant galaxy Hubble examined showed the same pattern. The light reaching Earth was stretched, elongated toward longer, redder wavelengths in a way that had a single, clean explanation. Those galaxies were moving away from us. The further they were, the faster they were going. This relationship, recession speed proportional to distance, became known as Hubble's law, and it is one of the most consequential measurements in the history of science. The immediate instinct is to picture this as an explosion, a central point, debris flying outward in all directions, galaxies as billiard balls launched through space, the most distant ones having travelled farthest because they were hit hardest. That picture is wrong, and the way it is wrong matters enormously. Galaxies are not moving through space away from us. Space itself is expanding, and the galaxies are riding inside it. The difference sounds subtle. It is not. Think of a loaf of bread rising in an oven. Embed raisins throughout the raw dough at various distances from each other. Now the dough rises. Every raisin moves away from every other raisin, not because the raisins are moving through the dough, but because the dough itself is expanding between them. A raisin that started twice as far away will end up moving away twice as fast, because there is twice as much dough expanding between it and you. There is no center raisin. No raisin is at the middle of the expansion. The expansion is the dough. Every raisin experiences the same thing. The elegance of this picture lies in its simplicity and its radical implications. The raisins do not need to be launched into motion. They do not need to push through the dough against any resistance. The expansion itself creates separation without requiring the raisins to move at all. Initial distance and recession speed are linked not through any force or velocity imparted to the raisins, but through the geometry of the expanding dough itself. The universe built this way requires no center, no launching point, no privileged location from which all things were sent outward. This is the universe. Space is the dough. Galaxies are the raisins. The expansion is not happening from a point. It is happening everywhere simultaneously, in every cubic meter of space, between every pair of galaxies, in all directions at once. There is no center to the expansion, no edge from which the expansion radiates outward, just stretching, uniform and relentless, built into the geometry of space itself. What Hubble had detected was not the movement of objects, it was the growth of the medium those objects inhabit. The redshift he observed was not a Doppler effect in the traditional sense, a galaxy speeding away the way an ambulance siren drops in pitch as it passes. It was a cosmological redshift. The wavelength of light stretched because the space it was travelling through stretched while the light was in transit. The light arrived longer than it left, and that lengthening told Hubble everything. This realization carried profound consequences for physics itself. It meant the universe was not a static container in which events occur, but rather a dynamic entity whose fundamental properties change over time. The expansion was not something superimposed on the universe from outside. It was woven into the fabric of existence, a property of space-time itself that Einstein's equations had permitted all along. Run this backward. If space is expanding now, it was smaller before. Further back, smaller still. Keep going, and the universe compresses into an extraordinarily small, extraordinarily hot, extraordinarily dense state. The physics break down before you reach a true beginning. General relativity stops being a reliable guide past a certain point, but the direction is clear. Everything we can see was once packed into a region that would make our entire observable universe look like the ocean compared to a single drop of water. Right forward instead, the universe was a certain size yesterday. It is larger today. It will be larger tomorrow. Not because new space is being manufactured somewhere and injected into the existing universe, because every region of existing space is itself expanding. The universe does not have an edge that is growing outward. The whole of it is growing, all at once, everywhere. When Hubble published his findings, the scientific community was not prepared for them. Einstein's own equations for general relativity had predicted a dynamic universe, one that could expand or contract, but Einstein had inserted a correction term, the cosmological constant, specifically to force the equations to produce a static universe. He believed, as nearly everyone did at the time, that the universe was fixed and eternal. Hubble's observation made that assumption untenable. Einstein later called the cosmological constant his greatest blunder. The universe had not been holding still. It had been growing the entire time, and nobody had been watching closely enough to notice. There is something worth sitting with here. Hubble made this discovery by studying the color of light from distant galaxies. By noticing a systematic shift so subtle it required careful spectroscopic analysis to confirm. From that shift, he deduced that space itself was not a neutral container, but an active participant, stretching and evolving. The scale of what that shift implied, the entire observable universe, 93 billion light-years across, growing continuously, came from examining the color of faint points of light on a photographic plate. That is the kind of measurement that earns its place in the history of science. The implication for size is immediate and significant. If the universe is expanding, it is larger now than it was when the light from the most distant galaxies began its journey toward us. By the time that ancient light arrives, the universe has been growing for the entire duration of the trip. The universe you are seeing when you look at distant galaxies is not the universe as it exists now. It is the universe as it existed when the light left. The universe of now is larger, substantially larger, than anything you are currently looking at. How much larger? That depends on how long the light has been traveling and how fast space has been expanding during the journey. For light that left nearly 13.8 billion years ago, the answer is dramatic. The math produces numbers that diverge sharply from naive intuition. But that is the next problem. For now, the critical thing to hold on to is simpler. The universe is not a fixed object sitting quietly in some larger container. It is growing. It has been growing since it began. It grows between now and the time you finish this sentence. The universe was bigger a second ago than it was a second before that, and it has been getting bigger continuously for nearly 14 billion years. If the universe is 13.8 billion years old and light can only travel so fast, shouldn't the edge of the observable universe be 13.8 billion light years away? It is a completely reasonable assumption. It is also wrong, not approximately wrong, not wrong in a minor technical sense, wrong by a factor that changes the entire picture of how large the cosmos actually is. Here is where the confusion starts. Most people hear the age of the universe, 13.8 billion years, and treat it like a speed calculation. Light has been traveling for 13.8 billion years, so the furthest it could have gone is 13.8 billion light years. Distance equals speed times time. The math seems clean. The problem is that the math assumes space stayed still while the light was moving. It did not. Space was expanding the entire time, and that changes everything. Think about what was actually happening when the oldest light in the universe began its journey. The Big Bang did not happen at a point and send matter flying outward into pre-existing empty space. Space itself was created in that event. In the earliest moments, everything that would become the observable universe was compressed into an extraordinarily small region. The galaxies, or rather the hot plasma that would eventually become galaxies, were not spread across billions of light years. They were packed together in a space far smaller than what exists today. When light left those early sources, it had a much shorter distance to cross, but space was not cooperating. The fabric of the cosmos was stretching in every direction, continuously, while the light was in transit. Picture an ant walking across a rubber band. The ant starts at one end and moves steadily towards the other. Now stretch the rubber band while the ant is walking. The ant still makes forward progress. It is still crossing real distance, but the far end of the rubber band is racing away. The ant can still reach it, provided the stretching is not too fast. When it finally arrives, though, the rubber band is far longer than it was when the ant set out. The starting point, the place where the ant began, is now much further from the endpoint than the ant's stride count alone would suggest. Light crossing the expanding universe works the same way. A photon leaving a distant source moves at a fixed speed through local space. Space itself, though, is stretching beneath it. The source that emitted the photon gets carried further away while the photon is in transit. By the time the photon reaches us, the galaxy that emitted it has been carried to a distance far greater than the light's travel time alone would imply. The most ancient light we can detect is the cosmic microwave background, a glow left over from roughly 380,000 years after the Big Bang, when the universe first became transparent. When that light began its journey, the region that emitted it was perhaps 40 million light years away from the region that would become Earth. Close by cosmic standards. That light has been traveling for nearly 13.8 billion years, but the source of that light, that shell of early plasma, has been carried outward by expansion the entire time. Today, that shell sits approximately 46 billion light-years distant. This is the number that surprises people, not 13.8 billion years of travel time. The source itself ended up 46 billion light-years distant. This is the number that surprises people, not 13.8 billion, not even 20 billion. 46 billion light-years is the radius of the observable universe. The diameter, the full width of the sphere of space from which light can reach us, is roughly 93 billion light-years. That is the observable universe, not the full universe, just the part we can see. Did we observe the demise of a star as it happened? The question astronomers kept asking in early 2020, when Betelgeuse dimmed, had that same character, something measurable pointing towards something vast and uncertain. The 46.5 billion light-year figure has the same quality. It is a number derived from careful measurement, from well-understood physics, from the same equations that predicted the existence of the cosmic microwave background before anyone detected it. This is not speculation dressed in mathematics. The expansion of space is real. The stretching of those photon paths is real. The consequence that the observable universe is roughly 7 times larger than a naive calculation would suggest is real. What makes this genuinely strange is that nothing violated the speed of light to produce this result. The photons always traveled at exactly the speed of light through their local piece of space. No rule was broken. No exotic physics was required. The expansion of space is not the same thing as motion through space, and that distinction is what allows the source of light to end up so much further away than the light's travel time implies. Space stretched. The light rode a moving platform without knowing it. The destination kept shifting. The photon arrived anyway. It is worth sitting with the numbers for a moment. A diameter of 93 billion light-years. 1 light-year is roughly 5.9 trillion miles, 93 billion of them end to end. The galaxy that emitted the oldest light we can see is now 46 billion light-years away and still moving. By the time any new light it emits today reaches us, if it reaches us at all, that galaxy will be further still. The universe is not a snapshot. It is a continuously moving target, and our best measurements tell us the target is moving faster every year. The calculation that gives 13.8 billion light-years is not meaningless. It reflects the age of the universe, the elapsed time since the Big Bang. That number is real and important. But distance and travel time are not the same thing in an expanding cosmos, and conflating them produces a universe that is 7 times too small. The actual observable universe, the sphere of space whose light has had time to reach us, is 46.5 billion light-years in radius, and the physics that produce that answer are not in serious dispute. The universe is not 13.8 billion light-years across. It is roughly 93 billion, and that gap is not a rounding error. In 1998, 2 separate teams of astronomers pointed their telescopes at distant exploding stars and came back with the same answer, an answer neither of them wanted. Both teams had set out to measure something they expected to be straightforward. The universe had been expanding since the Big Bang. Everyone knew that. The question was how fast that expansion was slowing down. Gravity pulls matter together. The collective gravity of everything in the universe should be acting as a brake on the expansion, tugging galaxies back toward each other, pulling the whole structure gradually inward. The expansion would still be happening, but it should be decelerating, coasting toward a slow and inevitable collapse, or a quiet, eternal drift. Both teams expected to measure that deceleration. They expected to confirm it. Instead, they found the opposite. The universe was not slowing down. It was speeding up. The tool they used was a specific type of exploding star called a Type Ia supernova. When a certain kind of white dwarf star accumulates too much mass, it crosses a precise threshold and detonates. The explosion always reaches roughly the same peak brightness. Always. This makes Type Ia supernovae extraordinarily useful. They are what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate the distance to it with precision. By measuring hundreds of supernovae across vast distances and comparing their apparent brightness to their redshift, both teams expected the data to tell a consistent story of slowing expansion. The data told a different story entirely. The distant supernovae were fainter than they should have been, fainter by a small but unmistakable margin. There was one explanation that fit. Those supernovae were farther away than the deceleration model predicted. Space between here and there had stretched more than it should have. The expansion had not been slowing down over the past several billion years. It had been accelerating. Both teams went back and checked their instruments. They checked their calibrations. They ran the numbers again. They looked for errors in the supernova selection, in the redshift measurements, in the corrections applied for dust and distance. Months passed. The answer did not change. In 1998, they published. The cosmological community, as one astronomer later described it, went into a kind of collective shock. Saul Perlmutter led one team, Brian Schmidt and Adam Rees the other. In 2011, all three received the Nobel Prize in Physics. The discovery of accelerating expansion is now considered one of the most consequential results in the history of observational astronomy. What it required, though, was an explanation. Something had to be driving that acceleration. Something had to be pushing the expansion faster and faster against the pull of gravity. The universe was not coasting. It was being driven. Astronomers gave the unknown cause a name. They called it dark energy. The name was chosen deliberately, honestly even, because it acknowledged how little was understood. Dark in this context means invisible and undetected. Energy because the math demanded something with energy to produce the observed effect. Dark energy. A label for a mystery. Here is the part that is genuinely strange. The leading candidate for dark energy is not a substance. It is not a particle. It is not a field traveling through space the way light does. The leading candidate is the cosmological constant, the idea that space itself has an intrinsic energy density, vacuum energy. Even in the most perfect empty space, with every particle and every wave of radiation removed, space itself carries energy, a fixed amount per unit volume, a baseline hum built into the fabric of the universe. Einstein had proposed something very like this a century ago, inserting a term into his equations of general relativity to prevent the universe from collapsing under its own gravity. He called it the cosmological constant. When Edwin Hubble demonstrated in 1929 that the universe was expanding rather than static, Einstein dropped the constant, reportedly calling it his greatest blunder. He had invented a stabilizing force the universe did not seem to need. Decades later, the data from those supernovae showed the universe did need something after all. Not to prevent collapse, to explain acceleration. Einstein's blunder turned out not to be a blunder. It was premature. The deep strangeness of dark energy as vacuum energy lies in what happens when space expands. As the universe grows, new space appears, and with new space comes new vacuum energy. The total amount of dark energy in the universe is not fixed. It grows as the universe grows. This is why the expansion accelerates rather than running out of steam. Ordinary energy dilutes as space expands. Pour a gas into a bigger container and its pressure drops. Vacuum energy does not dilute. It scales with volume. The more space there is, the more energy there is pushing space apart. The larger the universe gets, the faster it grows. This is a self-reinforcing process with no natural break. It does not slow down, it compounds. This is not the only candidate. Some physicists favor something called quintessence, a dynamic field whose energy density changes over time, unlike the fixed cosmological constant. Others suggest the acceleration might point to a breakdown in general relativity at the largest scales. Not an energy source at all, but a failure of the equations that predict how gravity works across billions of light years. Astronomers have continued measuring. The 2023 results from the Dark Energy Spectroscopic Instrument began probing whether the acceleration rate changes over time, which would distinguish a true cosmological constant from a dynamic field. The data is not yet definitive. The question remains open. What makes dark energy so unsettling is its dominance. Ordinary matter, everything you have ever seen, touched, or detected, accounts for roughly 5% of the total energy content of the universe. Dark matter, the invisible gravitational scaffolding that holds galaxies together, accounts for about 27%. Dark energy accounts for the remaining 68%. The component we understand least is the one that controls the fate of the universe. The universe is not mostly stars and galaxies and gas. It is mostly something we cannot see, cannot touch, and cannot fully explain. And that something is actively driving the universe toward a future of accelerating expansion without any sign of stopping. There is no known mechanism by which dark energy switches off. There is no theoretical reason to expect the acceleration to reverse. Whatever dark energy is, it is not going away, and it is the reason the universe will keep growing long after every star alive today has burned out. There is a boundary in the universe beyond which galaxies are already gone from us, even though we can still see some of their old light. This boundary has a name. Astronomers call it the cosmological event horizon, and it is one of the strangest consequences of living in an accelerating universe. It works like this. Space between any 2 points is not static, it stretches. And because dark energy keeps pushing that stretching faster and faster, there is a distance at which the space between us and a distant galaxy is expanding so rapidly that no signal, not a radio wave, not a photon of light, nothing can ever cross it to reach us. The galaxy is not moving through space at a speed exceeding light. The space itself is expanding faster than light can traverse it. That distinction matters. Nothing in relativity forbids space from expanding at any rate. Only objects moving through space at a speed exceeding light. The space itself is expanding faster than light can traverse it. That distinction matters. The expansion itself has no such ceiling. The result is a kind of cosmic shoreline. On one side, galaxies whose light can still reach us. On the other side, galaxies that are, for every practical purpose, permanently severed from our universe. Not destroyed, not gone in any physical sense. simply beyond the point of no return. The light they emit today will never arrive here. Their signals will travel toward us for billions of years and still fall short, carried backward by an expanding space faster than they can advance forward. What makes this genuinely difficult to absorb is that we cannot see the horizon directly. It does not announce itself. There is no visible line drawn across the sky, no dimming at the edge, no obvious marker. Some of the galaxies we observe tonight are already beyond it. Their old light that left them billions of years ago when the gap between us was smaller, is still arriving, still filling our telescopes with information. But if those same galaxies emitted a new signal today, that signal would never reach us. We are receiving their history. We will never receive their present. The current cosmological event horizon sits at roughly 16 billion light-years from Earth. Any galaxy beyond that distance is already cut off, and because the expansion is accelerating, that boundary is not static. It is shrinking relative to the observable universe. More galaxies are crossing it all the time, not because they are moving outward, but because the expansion is pulling them past the threshold faster than it used to. This process is relentless and inevitable under the influence of dark energy. The horizon does not hesitate or fluctuate. It advances according to the physics of expansion, pulling distant galaxies beyond observation as surely as a tide withdraws from shore. And unlike a tide, there is no returning mechanism. Once a galaxy crosses that threshold, it stays crossed. Project this forward and the picture becomes stark. In a few 100 billion years, almost every galaxy we can currently see will have crossed that boundary. The Virgo cluster, the Coma cluster, the great filaments and walls of the cosmic web, all of it will have receded beyond any possibility of observation. What remains visible will shrink to something far more modest. The local group, the Milky Way, Andromeda, and a handful of smaller satellite galaxies will still be gravitationally bound together, held by the force of their mutual attraction against the outward push of expansion. Everything else will be gone. Future astronomers, if any exist in that era, will live in a universe that appears almost entirely empty. A single merged galaxy surrounded by darkness in every direction. No other galaxies on the horizon. No evidence of expansion, because the only structures still present will be gravitationally locked together and not receding at all. They will look outward and see nothing. They may conclude they inhabit a solitary island in a static, featureless cosmos. They will have no way of knowing there are 2 trillion other galaxies out there, simply invisible, forever beyond any instrument they could build. They will be completely wrong about the nature of the universe, and nothing they can observe will tell them so. This is not a remote philosophical concern. It is the predictable future of a universe dominated by dark energy. The evidence of the Big Bang, the large-scale structure, the expansion itself, all of it is written in light that is still crossing the sky today. In that distant era, the cosmic microwave background will have stretched so far it becomes undetectable. The signals that taught us the universe is 13.8 billion years old and geometrically flat and built from a near-uniform plasma will have diluted beyond any receiver's ability to measure. The chapters of cosmic history that we have read will close, not because the history ends, but because the evidence disperses past the point of recovery. This is worth sitting with for a moment. We did not design telescopes capable of capturing the cosmic microwave background because we planned ahead. We built them, and the signal was there. we did not arrange for 2 trillion galaxies to be close enough to observe. We opened our eyes, and there they were. The conditions that allow a civilization to understand the scale and age and composition of the universe are conditions that exist only in a narrow window of cosmic time. Too early, and the universe is too hot and opaque to read. Too late, and the evidence has vanished behind expanding horizons. We happen to exist precisely during the window when the universe is fully legible. The cosmic microwave background is detectable. Distant galaxies are visible. The expansion is measurable. The entire history of the cosmos, from its first moments to the present, is written in light that is currently crossing space and arriving in our instruments. No civilization that comes after us, not by 1 billion years, not by 10 billion, will have access to the same record. They will see less. They will know less, not because they are less capable, but because the universe will have moved the evidence past the horizon. We live, without having earned it, in the moment of maximum cosmic visibility, and it will not last. The edge of the observable universe is not a wall. There is no boundary where space stops, no surface where matter ends and nothing begins. What sits at that horizon is something stranger and more unsettling than a wall. It is simply the point beyond which light has not had enough time to reach us. The universe on the other side of that line has been there for 13.8 billion years. It has been generating light, forming stars, pulling gas into galaxies through gravity. It has been doing everything the universe does. We just cannot see any of it yet because the light is still traveling. Think about what the observable universe actually shows us when we look in every direction. Galaxies appear in the same rough density whether you point a telescope north or south, toward Orion or away from it. The types of structures repeat, the same filaments, the same voids, the same distribution of matter, the same physics operating in the same way everywhere the signal reaches. No direction shows a thinning, a boundary effect, a fade toward empty space. The universe, as far as every instrument we have ever built can determine, does not know it is approaching any kind of edge. It just continues. This is what cosmologists call the cosmological principle. It is not an assumption pulled from thin air. It is the conclusion that falls out of every measurement made at the largest scales. The universe is homogeneous. It is isotropic. Every large region of it looks like every other large region. And if that principle holds beyond the observational horizon, which there is no physical reason to doubt, then the universe outside our bubble looks like the universe inside it. More galaxies, more stars, more planets orbiting those stars in the dark. The number of stars inside the observable universe alone is already difficult to express. Estimates land around 1 septillion, that is the number 1, followed by 24 zeros. If you tried to count them at a rate of 1 per second, you would need longer than the current age of the universe just to make a dent. That number is not the count of all stars in existence. It is the count of the stars in the portion of space we happen to be able to see. Beyond the horizon, if the density holds even roughly constant, the count keeps climbing in the same way. Double the volume and you double the stars. Triple it and you triple them. If the universe extends even a few times further than our observable sphere, the true stellar count is already so large the number stops functioning as information. There is a particular strangeness in considering what sits just beyond the horizon. Not billions of light years beyond it, just past it, by a few 100 million light years or less. The galaxies out there are almost certainly unremarkable. Clusters of hundreds of billions of stars each, arranged in the same web of filaments and voids we see everywhere else, lit by the same physical processes that light every galaxy we can see. Some of those galaxies have been emitting light for billions of years that is heading directly toward us right now, crossing the intervening space, and has simply not arrived yet. In a billion years, light from some of those galaxies will finally cross our horizon and become observable. The universe does not expand the visible region by growing. It expands it by letting the existing universe reveal itself over time. This also means the boundary is not fixed. The observable universe is not a static sphere locked at a particular size. As time passes, light from more distant regions continues arriving. Were observers here in 10 billion years, if any exist, they would, in principle, have access to signals from regions we will never see. The observable universe has been growing since the first light traveled anywhere, and it would keep growing in this sense even if expansion were not accelerating. The horizon is a moving line. What lies beyond it today is simply today's mystery, not a permanent unknown. What makes this hard to hold in the mind is that the universe beyond the horizon is not hypothetical in the way a multiverse is hypothetical. It is not the product of a speculative theory or an interpretation of mathematics. It is simply more of the universe that already exists, operating under the same equations, shaped by the same constants, containing the same elements arranged by the same gravitational physics. When physicists say they believe the universe extends beyond our observable sphere, they are not guessing. They are applying what works everywhere we can check and noting that there is no physical mechanism that would cause it to stop working just past the edge of our view. The size implied by even conservative estimates is severe. If the universe is merely somewhat larger than what inflation models require as a minimum, and inflation models already imply something vastly larger than the observable sphere, then the number of stars in existence is not 1 septillion. It is a number that requires a different framework entirely to discuss. There is a point at which scale stops being descriptive and becomes something closer to philosophical. The universe does not become less real when numbers about it stop being usable. It just becomes a thing that exists at a size beyond what human intuition was built to process. Some estimates, depending on assumptions about inflation and global geometry, place the total size of the universe at 10 to the 23rd times the volume of the observable sphere. Others go further. None of these numbers are confirmed. None of them can be confirmed with any instrument we can currently build or conceive of building. But the direction all the evidence points is consistent. There is more out there, far more, and the observable universe is a small sample of it in the same way that a single city block is a small sample of Earth. The block is real. The rest of Earth is real. The block just cannot see the rest. The honest summary is simple. Nothing in physics predicts an edge to space at our cosmic horizon. Nothing in the data suggests the universe behaves differently beyond the boundary of what we can observe. The uniformity is so consistent across the entire observable volume that the inference extends naturally beyond it. Beyond our horizon, as best we can tell, there is more universe. The same universe, following the same rules, stretching on in ways we may never be able to measure. In the first fraction of a second after the Big Bang, a fraction so small it requires a negative exponent with 32 zeros, something happened that makes everything else in the history of the universe look modest. This is the theory of cosmic inflation. The basic claim is extraordinary enough, but it is worth sitting with before moving on. In somewhere around 10 to the negative 32 seconds, a window of time so brief that no human analogy does it justice, the universe expanded by a factor of at least 10 to the 26. Some estimates put the factor much higher. A region of space smaller than a proton, bloated to roughly the size of a marble. That marble is everything we can observe. Every galaxy, every light year, every structure in that 93 billion light-year bubble we call the observable universe traces back to something smaller than the nucleus of an atom. The expansion that happened in that fraction of a second dwarfs everything the universe has done in the 13.8 billion years since. The theory was not invented to make the universe sound dramatic. It was invented to solve problems. Serious ones. Problems that the standard Big Bang model, on its own, simply could not answer. The first is called the horizon problem. Look in one direction across the observable universe, out to the cosmic microwave background, the oldest light we can detect, and you see a temperature of about 2.7 Kelvin. Now look in the exact opposite direction. Same temperature, accurate to 1 part in 100,000. This is true no matter which two opposite points you pick. The entire sky is uniform to a degree that should not be possible. Regions on opposite sides of the observable universe are separated by 93 billion light years. They have never been in contact. Light has not had time to travel between them, not even in 13.8 billion years. So how do they know to be the same temperature? Without inflation, there is no answer. Two people who have never communicated cannot agree on the same number by accident, not 100,000 times in a row. Inflation solves it cleanly. Before the expansion event, that entire region of space was tiny enough that all parts of it were in contact, all in thermal equilibrium. The expansion then stretched that uniform region to cosmic scales. The uniformity was baked in before inflation happened. After inflation, the sky looks the same in every direction because it came from a single connected region that had time to even out. The second problem is the flatness problem, the geometry of the universe. The question of whether space curves back on itself, curves outward, or lies flat, is sensitive to the density of matter and energy in the earliest moments. For the universe to be as flat as we measure it today, the density at the Planck epoch had to be tuned to roughly 1 part in 10 to the 60. That is not a reasonable coincidence. A universe slightly too dense curves and collapses. A universe slightly too sparse curves outward and expands so fast it never forms structure. The universe we live in sits on the razor's edge between these outcomes. Inflation explains this because exponential expansion flattens geometry the same way blowing up a balloon flattens its surface. Whatever curvature the universe had before inflation, the expansion erased it. A small patch of curved space, stretched by a factor of 10 to the 26, becomes indistinguishable from flat. The third problem involves magnetic monopoles. Early universe physics predicts that certain exotic particles, magnetic monopoles, objects with only a single magnetic pole, should have been produced in enormous quantities in the first moments after the Big Bang. We have never detected a single one. If they were produced, where did they go? Inflation dilutes them to such a low density that the probability of finding one in the observable universe drops to essentially zero. The monopoles were not destroyed. They were simply spread across a volume of space so vast that we will almost certainly never encounter one. 3 separate problems, one solution. This is the kind of explanatory power that makes a theory worth taking seriously. Alan Guth proposed the original version of inflation in 1980. Andre Linde and others refined it into the forms that physicists work with today. The theory is not proven in the way a lab experiment is proven, but it is supported by predictions that checked out. The flatness we measure is consistent with inflation. The uniformity of the microwave background is consistent with inflation. The tiny quantum fluctuations that inflation would have produced and then stretched to cosmic scales match the temperature variations in the CMB with remarkable precision. Now consider what inflation implies for the total size of the universe. Start with the observable universe, 93 billion light-years across, containing 2 trillion galaxies, an estimated 1 septillion stars. This entire structure descended from a region smaller than a proton. Inflation stretched that region by at least 10 to the 26. But inflation did not stop neatly at the borders of what we can observe. The mathematics of inflationary models suggests that the expansion affected a region far larger than the patch that became our observable universe. The observable universe is not the product of all the inflation that occurred. It is the product of a small piece of it. Most conservative estimates put the total size of the post-inflationary universe at least 10 to the 23 times larger than the observable universe. Read that number carefully. 10 to the 23 is 100 sextillion. If you took the observable universe, 93 billion light-years of galaxies, and used it as a single unit, you would need 100 sextillion of those units laid end to end to span the full extent of what inflation likely produced. And this is considered conservative. Some models produce factors that are vastly larger. The observable universe in this picture is not a large place sitting inside a slightly larger place. It is an almost imperceptibly small region inside something that the word enormous fails to describe. There is no edge to what inflation produced, no wall where the expansion stopped and space ended. Beyond our observable bubble, the same physics apply. The same types of structures almost certainly exist. The same rules govern matter and energy. But we cannot confirm any of it directly. The information is not available. Our cosmic horizon cuts off the view before we can see any of it. This is the strange position inflation puts us in. The theory solves problems that no other explanation touches. Its predictions match what we measure, and if it is right, we live inside what amounts to a rounding error, a microscopic sliver of the actual universe, surrounded in every direction by space we can never reach, light we can never receive, and structure we can never map. Inflation did not just make the universe big, it made the observable universe a rounding error inside the total universe. The universe has a shape, and we can measure it. That sentence sounds simple. It is not. The shape of the universe is not the shape of the objects inside it, not the spiral arms of galaxies or the curve of a planet's surface. It is something deeper. It is the geometry of space itself, the way parallel lines behave across cosmic distances, the way angles add up in triangles drawn not on paper, but across billions of light-years of actual reality. And depending on which shape turns out to be correct, the universe either ends or it doesn't. There are 3 possibilities. The first is a positively curved universe. Think of the surface of a sphere. Draw a triangle on that surface, connect 3 points, and the angles inside that triangle will add up to more than 180 degrees. Lines that start out parallel will eventually converge. A universe with positive curvature wraps back on itself. If you traveled in one direction long enough, you would eventually return to where you started. This kind of universe is finite. It has a total volume. It has a size you could, in principle, measure. It does not have an edge. There is no wall to run into, but it is bounded, the way a sphere's surface is bounded without having a border. The second possibility is a negatively curved universe. Think of a saddle, the kind you put on a horse. Draw a triangle on that surface, and the angles add up to less than 180 degrees. Parallel lines diverge. Space bends outward rather than inward. A negatively curved universe is infinite. It extends without limit in every direction, and the geometry of it is stranger than anything flat. Most people have no intuition for what negative curvature feels like at large scales, because nothing in daily human experience looks that way. The third possibility is a flat universe. Euclidean geometry. Parallel lines stay parallel forever. Triangles add up to exactly 180 degrees. Space extends without bending, without curving back, without any deviation from the geometry you learned as a child. A flat universe can be either infinite or extremely large but finite, depending on its topology. The flatness itself does not force a verdict, but it leans heavily in one direction. Now here is how astronomers actually measure this. The cosmic microwave background, the oldest light in the universe, has fluctuations printed across it. Patches of slightly different temperature spread across the whole sky. Those patches have a characteristic angular size. How large they appear in the sky depends on the geometry of the space the light traveled through to reach us. A positively curved universe would magnify them. A negatively curved universe would shrink them. A flat universe would leave them at a specific predicted size. The Planck satellite, which produced the most detailed map of the microwave background ever assembled, measured those angular sizes with extraordinary precision. The result: the universe is flat to within 0.4%. Not approximately flat, not roughly flat, flat to a fraction of a percent, which is the precision limit of the measurement itself. What does 0.4% mean in practice? It means there is a small residual uncertainty. The universe could have a slight curvature we haven't detected yet. Better instruments might find it. But as things stand, every measurement points to flat, and the margin is razor thin. If the universe is truly flat, not just close to flat, but genuinely, exactly flat, then it is almost certainly infinite. A perfectly flat universe that is finite requires very specific topological conditions that there is currently no evidence for. The simplest interpretation of a flat universe is a universe without limit. No edge, no center, no boundary in any direction, just space, continuing. That is where the numbers stop working as numbers. An infinite universe does not mean a very large universe. It does not mean the largest number you can imagine, plus more. It means the quantity is without bound. There is no final galaxy. There is no last stretch of void before things give out. It goes on. And if it goes on, something follows from that, something almost too large to sit with quietly. Matter in the universe is distributed according to physical laws. Quantum mechanics limits how many distinct configurations of matter can exist within any given volume of space. The number of possible configurations is extraordinarily large, but it is finite. In an infinite universe, every possible configuration of matter occurs. Not might occur, occurs. Infinitely many times. This means there are other solar systems, there are almost certainly other Earth-like planets. There are, by the strict logic of infinite space combined with finite configurations, other solar systems that are exact copies of ours. Other Earths with the same continents, the same oceans, the same history played out identically. Other people having the same conversation at distances so vast the light will never bridge the gap between us and them. This is not a thought experiment. This is not metaphor. This is what infinite space with matter in it mathematically requires. The copies are not in another dimension. They are in this universe, just unimaginably far away, beyond any horizon, separated by distances that make our observable universe look microscopic. The nearest copy of Earth, by some estimates, would be roughly 10 to the power of 10 to the power of 28 meters away. That number is not useful as a number. It is useful only as an impression, unreachably far, in a universe that has the room for it. None of this is confirmed. The 0.4% margin in our flatness measurement leaves enough room, technically, for a universe that is curved, finite, and free of all these implications. A more curved universe would be smaller, perhaps only a few times larger than what we can observe. The infinite copies would not exist. The universe would have a size. Future measurements may close that margin further. They may not. For now, all we can say is that every tool we have pointed at the geometry of space has come back with the same answer. Flat, as far as we can tell. In every direction we can check. An infinite universe is not a comforting thought, exactly, but it is consistent with everything we currently know. The multiverse is not a fringe idea. It is what you get when you take the most successful theories in physics and follow them past the edge of what we can observe. That distinction matters. The multiverse did not emerge from wishful thinking or from physicists who decided the universe was too small and wanted more of it. It emerged from the equations. 3 separate branches of modern physics, developed independently, following completely different lines of reasoning. Each arrived at the same unsettling conclusion. What we can see is almost certainly not all there is. When 3 different roads lead to the same place, that is worth paying attention to. The first road runs through inflation. Earlier in this video, inflation was the theory that the universe expanded at a staggering rate in its first fraction of a second, a region smaller than a proton becoming everything we can observe across 93 billion light-years of space. The physicist Alan Guth proposed the basic framework. Andre Linde extended it, and what Linde found in the mathematics was deeply strange. Once inflation starts, it does not necessarily stop everywhere at once. In most models, inflation is like a fire that keeps igniting new patches of space even as it dies out in others. Our universe is a region where inflation ended, cooled, and produced the conditions we live in. But out beyond our horizon, inflation may still be running. It may have been running continuously since the beginning, spawning new bubble universes at a rate that never slows. Each bubble inflates into its own universe with its own physical properties. The constants that define physics, the strength of gravity, the mass of the electron, the cosmological constant, are not necessarily identical across all bubbles. They may vary. What that means is this: the universe that produced chemistry and stars and life is one bubble among a potentially infinite sea of them, and most of those bubbles may be nothing like ours. This version of the multiverse is called eternal inflation, and it follows directly from the same mathematics that explains why the observable universe is flat and uniform. It was not invented to make the cosmos more dramatic. It came with the theory. The second road runs through quantum mechanics. At the smallest scales of physical reality, particles do not behave the way objects do in everyday experience. Before a quantum event is measured, a particle does not have a single definite state. It exists in a superposition of all its possible states simultaneously. When a measurement occurs, one outcome appears. The question that has divided physicists for nearly a century is, what happened to the other outcomes? The standard answer, the Copenhagen interpretation, says the other possibilities simply ceased to exist at the moment of measurement. But in 1957, a physicist named Hugh Everett proposed a different answer. Nothing disappears. Every possible outcome occurs. Reality branches. Each branch continues forward as its own separate world, unaware of the others. This is the many worlds interpretation, and by the standards of modern physics, it is not a marginal position. It is taken seriously by a significant fraction of working physicists. The branching is not occasional. Every quantum interaction, anywhere in the universe, at every moment produces new branches. The number of branches grows exponentially. There is no clean way to count them. The resulting structure is incomprehensibly large. Not large in the way the observable universe is large, but large in a way that makes the observable universe look like a single atom inside it. Whether you find this profound or absurd depends largely on how comfortable you are with mathematics that refuses to be pictured. The third road runs through string theory. String theory attempts to unify all the fundamental forces of nature into a single framework by proposing that the smallest constituents of reality are not point-like particles, but tiny, vibrating strings of energy. The different ways these strings can vibrate correspond to different particles. The mathematics of string theory is extraordinarily complex and has produced results that physicists have spent decades trying to interpret. One of those results is what is called the landscape. String theory does not produce a single unique set of physical laws. It produces an enormous number of possible configurations, roughly 10 to the power of 500 distinct solutions, each corresponding to a universe with its own particle masses, force strengths, and physical constants. That number, 10 to the 500, is so far beyond human comprehension that calling it astronomical would be an insult to astronomy. If each of those configurations corresponds to a real universe, then the multiverse is not just large, it is almost incomprehensibly varied. The laws of physics that seem fundamental to us, fixed, universal, necessary, may be nothing more than the local rules of our particular configuration. None of this is settled. That point deserves to be stated plainly. Multiverse theories are among the most contested ideas in modern physics, and the criticism is not coming from people who haven't thought carefully about the subject. The core objection is scientific rather than philosophical. A theory that predicts things you can never test is not doing the same job as a theory that predicts things you can measure. If other bubble universes are permanently beyond our horizon, if other quantum branches are fundamentally inaccessible, if other string vacua are separated from ours by barriers that cannot be crossed, then what does it mean to say they exist? Some physicists consider this a fatal flaw. Others argue that untestability is a limitation of our instruments, not a failure of the theory. The debate is genuine, and it has not been resolved. What is harder to dismiss is where these ideas came from. Eternal inflation was not invented to produce other universes. It was proposed to solve specific problems in standard cosmology. and the multiverse came along as an uninvited consequence. The many worlds interpretation was not proposed because Everett wanted infinite worlds. It was proposed because the mathematics of quantum mechanics, taken literally and without any additional assumptions, produced branching. The string landscape was not designed to be vast. It emerged from attempts to find a unified theory of physics. In each case, physicists followed the equations, and the equations pointed outward, past what we can observe, into something larger. The universe, taken seriously, keeps producing more universe. Whether or not other universes are real, the fact that our best theories keep producing them is something physicists are going to have to reckon with. Measuring the distance to a nearby star is hard enough. Measuring the distance to a galaxy billions of light years away required building a chain of methods, each one dependent on the one below it. The chain has a name. Astronomers call it the cosmic distance ladder, and it is one of the great engineering achievements of modern science. Not engineering with metal and circuits, but with geometry, physics, and a century of careful observation stacked on top of itself. Each rung of the ladder reaches a little further than the last. Each one is anchored to the rung below it. Pull out one rung, and everything above it collapses. The first rung is the simplest. Hold a finger in front of your face and close one eye, then switch eyes. Your finger appears to jump against the background. That apparent shift is parallax. Stars do the same thing. As Earth moves around the Sun across 6 months, a nearby star appears to shift slightly against the more distant stars behind it. The amount of shift tells you the distance. No assumptions required, no physical models, just geometry. This method works cleanly out to a few thousand light years. Beyond that, the shifts become too small to measure reliably, even with the most precise instruments we have ever built. So astronomers needed something brighter, something visible across greater distances, something whose true luminosity they could know in advance. They found it in a strange class of stars that pulse. Cepheid variable stars expand and contract on regular cycles, and as they do, they brighten and dim. In 1908, a Harvard astronomer named Henrietta Leavitt noticed something while cataloguing stars in the Magellanic Clouds. The slower a Cepheid pulsed, the intrinsically brighter it was. The relationship was clean and consistent. If you measured how long a Cepheid took to complete one cycle, you knew its true brightness. Compare that to how bright it appeared from Earth, and you had its distance. This discovery is sometimes called one of the most consequential measurements in the history of astronomy, and that is not an overstatement. Edwin Hubble used Cepheids to show that certain fuzzy patches in the sky were not clouds of gas inside our galaxy. They were entire galaxies far beyond it. The universe expanded overnight, conceptually, because of what Henrietta Leavitt noticed in a table of numbers. Cepheids are bright enough to see across tens of millions of light years, but the universe is billions of light years deep. Astronomers needed a brighter rung still. They found one in catastrophe. Certain dying stars, a specific type called Type Ia supernovae, always explode with almost exactly the same intrinsic brightness. The physics behind this consistency is elegant. A white dwarf star slowly accumulates mass from a companion star. When it crosses a precise mass threshold, it ignites in a runaway nuclear reaction. The same mass, the same trigger, the same explosion, every time. Because astronomers know how bright these blasts truly are, they can measure how bright they appear and calculate the distance. Type Ia supernovae are visible across billions of light years. They are the best standard candles in the universe. They are also what two independent research teams were studying in 1998 when both came back with the same impossible result. The universe's expansion was not slowing down. It was accelerating. That discovery revealed dark energy. Beyond even supernovae, astronomers lean on redshift and the relationship that Hubble himself worked out. Galaxies moving away from us have their light stretched toward the red end of the spectrum. The faster the recession, the greater the stretch. Once the distance ladder is calibrated using Cepheids and supernovae, astronomers can read a galaxy's redshift and convert it directly into distance. This works across the full depth of the observable universe, out to the most ancient light we can detect. Were it not for the lower rungs, this one would be useless. Redshift gives you velocity. To turn velocity into distance, you need to know the expansion rate, a number called the Hubble constant. And here the ladder develops a crack. Different methods of measuring the Hubble constant keep producing different answers. Teams that calculate it using the cosmic microwave background, the oldest light in the universe, arrive at roughly 67 kilometers per second per megaparsec. Teams that measure it using Cepheids and supernovae in the local universe arrive at closer to 73. That gap is small in everyday terms. In cosmology, it is a serious problem. Both measurements have been checked repeatedly. Both teams have looked for errors. The discrepancy persists. Astronomers call this the Hubble tension, and it has become one of the most discussed puzzles in the field. There are two broad camps. The first holds that some systematic error is hiding somewhere in the ladder, a miscalibration at one of the lower rungs that propagates upward and skews the final number. Find the error, fix it, and the tension resolves. The second camp holds something more unsettling. What if there is no error? What if the measurements are correct, and the disagreement reflects something genuinely unknown about the universe? New physics. Some process in the early universe that standard models do not include. A property of dark energy that changes over time rather than staying constant. The tension on this reading is not a mistake. It is a signal. This matters enormously for questions of scale. The Hubble constant is not just an abstract number in an equation. It sets the conversion between redshift and distance for every galaxy we cannot reach by other means. A difference of several kilometers per second per megaparsec sounds trivial. Compounded across billions of light years, it shifts distance estimates significantly. If the true value of the expansion rate is uncertain, then the distances to the most remote objects in our observable universe are uncertain. The size of the observable universe is uncertain. Not wildly uncertain, not enough to throw out the 93 billion light-year figure, but uncertain in ways that matter to precision cosmology. The chain works well enough to produce confident answers at the largest scales, but the small uncertainty at each rung compounds, and at cosmic distances, small uncertainties become large ones. About 380,000 years after the Big Bang, the universe did something it had never done before. It became transparent. Before that moment, space was a wall. Not a wall you could point to or fly toward, but a wall of physics. A dense, hot plasma so tightly packed that light could not move through it. Photons would travel a short distance and immediately collide with a free electron, scatter, travel again, collide again. The universe was opaque the way the inside of a star is opaque. No beam of light could cross any meaningful distance. If you had existed then and somehow survived the heat, you would have seen nothing. Not darkness, something closer to blindness. Light everywhere going nowhere. Then the temperature dropped far enough, around 3000 Kelvin. Electrons slowed down, protons pulled them in. Hydrogen atoms formed for the first time, and the free electrons that had been blocking every photon's path were suddenly gone, locked inside atoms. The fog cleared. Light that had been scattering and bouncing for hundreds of thousands of years was finally free to travel. It streamed outward in every direction at once. That release, that single moment of transparency, is what we call recombination. And the light it produced has been traveling ever since. We can detect it right now, today, coming from every direction in the sky simultaneously at a temperature of 2.7 Kelvin, just barely above absolute zero. That temperature is what 380,000-year-old light looks like after 13.8 billion years of expansion have stretched it from visible wavelengths down into microwaves. It is called the cosmic microwave background, and it is the oldest light in the observable universe. There is no older light. There cannot be. Everything before recombination is hidden behind that opaque plasma wall, inaccessible to any telescope that works with photons. The two physicists who first detected it, Arno Penzias and Robert Wilson, did not know what they had found. In 1965, they were using a large horn antenna in New Jersey and kept picking up a persistent hiss, a low-level noise that appeared in every direction they pointed. They checked the equipment. They removed pigeons nesting in the antenna and cleaned out what they politely described as a white dielectric material. The noise remained. It was coming from the sky itself. What they had stumbled into was the afterglow of the Big Bang. They won the Nobel Prize in Physics in 1978. Here is what makes the CMB remarkable beyond its age. It is almost perfectly uniform. In every direction, the temperature is 2.7 Kelvin, with variations so small that early instruments could not even detect them. But almost uniform is not the same as perfectly uniform. When measurements became precise enough, the fluctuations emerged, tiny ripples in temperature, 1 part in 100,000. Warmer patches, cooler patches, each one a fraction of a degree different from the average. These are not instrument errors. They are real, and they are the most important imperfections in the history of the universe. Those fluctuations were density variations in the early plasma. Regions slightly denser than average, regions slightly thinner. When recombination happened, those variations were frozen into the light like a photograph of the infant universe taken at 1/10,000th of a second of exposure. Over the following billions of years, gravity amplified those tiny overdensities. Matter fell toward the denser regions, piled up, formed the first stars, the first galaxies, the long filaments of the cosmic web. The universe you see today, with its clusters and voids and walls of galaxies, grew out of fluctuations smaller than 1 part in 100,000. The entire large-scale structure of the cosmos traces back to those ripples in the CMB. This is not a metaphor. The seeds are measurable. The grown structures are measurable. The relationship between them matches what physicists predict, and that agreement is one of the strongest confirmations that our model of cosmology is essentially correct. The fluctuations do something else. They tell us the geometry of the universe. The physics of that early plasma produced pressure waves, sound waves essentially, propagating through the hot gas before recombination. Those waves left a characteristic imprint on the CMB, hot and cold spots that tend to cluster around a preferred angular size in the sky, roughly 1 degree across. That angular size depends on how far the sound waves travelled before recombination froze them, and on the geometry of the space the light crossed to reach us. In a positively curved universe, the spots would appear larger. In a negatively curved universe, smaller. In a flat universe, the spots appear at exactly the angular size the physics predicts. When astronomers measure the CMB, the spots appear at that predicted size. The universe is flat, or so close to flat that any curvature is below the precision of our measurements. The Planck satellite, launched by the European Space Agency in 2009, produced the most detailed map of the CMB ever assembled. Its measurements of those temperature fluctuations confirmed the universe's age at 13.8 billion years, its composition as roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, and its geometry as flat to within a fraction of a percent. These are not estimates. They are the most precisely measured numbers in cosmology, extracted from the oldest light we can see. But here is what the CMB is not. It is not a boundary. It is not the edge of space. The plasma wall that produced it was not a surface surrounding empty nothingness. It was a surface surrounding more plasma, more space, more universe. That universe extended beyond the region we can see then, and it extends beyond it now. The CMB marks the limit of what light can show us. It does not mark the limit of what exists. Space continued past that photon horizon in 380,000 CE, and it continues past our observable horizon today. The CMB is the wall of our vision, not the wall of reality. What lies beyond it follows the same physics, the same matter distribution, the same geometry. There is no reason to expect the universe to stop at the place where our tools run out. The CMB is not the edge of the universe. It is the earliest photograph we can take of it, and what it shows is a universe already far larger than what any of us were taught. Zoom out far enough from any individual galaxy, and the universe stops looking random. What you see instead is something that nobody fully anticipated before the computer simulations and sky surveys of the late 20th century made it visible. Matter in the universe, all the gas, all the stars, all the galaxies, is arranged into a structure, a vast interconnected architecture of threads and sheets and enormous empty spaces, stretching across scales that make individual galaxies look like dust motes. Astronomers call it the cosmic web, and once you have seen a map of it, you cannot unsee it. The basic picture is this. Galaxies do not scatter randomly through space the way a handful of sand thrown in a room might scatter. They cluster. They gather into groups, and those groups gather into clusters, and those clusters are strung along filaments hundreds of millions of light years long. Between the filaments lie voids, vast stretches of near-empty space, hundreds of millions of light years across, containing almost nothing. No galaxies, no gas to speak of, just space. The filaments form the bright skeleton of the web. The voids form the dark gaps between the threads. Together, they produce something that looks, at the largest scales, less like a physics problem and more like something grown. The largest known structures in the universe are these filaments and walls. The Hercules Corona Borealis Great Wall is roughly 10 billion light years across. Let that number sit for a moment. The observable universe is about 93 billion light-years in diameter, and a single structure within it spans more than 10% of that width. Structures like the Hercules Corona Borealis Great Wall are genuinely problematic for cosmologists because the standard model of cosmology assumes that at the very largest scales, matter should be distributed uniformly. That assumption is called the cosmological principle. A structure 10 billion light-years wide challenges it directly. Either the universe needed far more time than expected to grow something so large, or there is something about the early universe that produced structure faster than the standard models allow. The debate over what the Great Wall means is not settled. Closer to home, our own position in this web has been mapped with some precision. The Milky Way belongs to a supercluster of galaxies called Laniakea. The name comes from Hawaiian, meaning immeasurable heaven. It was formally identified and mapped in 2014 by a team led by astronomer Brent Tully, using data on the motions of thousands of galaxies. Laniakea spans roughly 500 million light-years across its widest dimension. It contains the mass of approximately 100 million billion suns, and it encompasses around 100,000 galaxies, including our own. The Milky Way sits near the outer edge of Laniakea, not anywhere close to its center. At the center lies a gravitational focal point called the Great Attractor, a region of high mass density toward which everything in the supercluster is slowly flowing, including us. Not quickly, not perceptibly in any human lifetime, but our galaxy and everything around it is drifting at hundreds of kilometers per second toward a point we will never reach, because the overall expansion of the universe is carrying the Great Attractor away from us at the same time we fall toward it. The web did not always look like this. In the early universe, the distribution of matter was far smoother. The cosmic microwave background shows us just how smooth. Tiny fluctuations of about 1 part in 100,000, barely any structure at all. But gravity is relentless, and over billions of years, those tiny variations were enough. Regions slightly denser than average pulled matter toward themselves. Slightly underdense regions lost matter to their denser neighbors. Over hundreds of millions of years, small concentrations grew into galaxies. Galaxies gathered into clusters. Clusters were drawn along lines of gravitational attraction between them, forming the filaments. The underdense regions expanded outward into voids. The web assembled itself gradually out of nearly nothing, driven by gravity working on tiny initial fluctuations over nearly the entire age of the universe. Dark matter is the scaffolding that made this possible. Ordinary matter, all the gas and stars, comprises only about 5% of the universe's total energy content. Dark matter comprises roughly 27%. It does not emit light. It does not interact with light, but it responds to gravity and produces gravity, and in the early universe it began clumping together well before ordinary matter could. By the time ordinary matter was free to move, dark matter had already sketched out the rough architecture, halos and filaments and walls of invisible mass. Ordinary matter simply fell into those structures, following the gravitational blueprint left by dark matter. Stars formed, galaxies lit up, the cosmic web became visible because ordinary matter traced the invisible web that dark matter had already built. What we see in galaxy surveys is only the illuminated surface of a deeper structure we cannot directly observe. The scale of the voids is as striking as the scale of the filaments. The Boötes void, for instance, spans roughly 330 million light-years. That is not a region with fewer galaxies. That is a region with almost no galaxies at all. A nearly spherical bubble of space, 330 million light-years across, largely empty. The filaments surrounding such voids contain thousands of galaxies packed into sheets and threads. The contrast between the filaments and the voids is one of the most visually striking features of any large-scale map of the universe. The web looks almost cellular, like foam on a microscopic scale. Thin, bright walls surrounding dark, empty interiors. It also resembles, depending on who you ask, the branching structure of neurons in the brain, or the network of roots from a plant spread through soil. No one is suggesting these resemblances are more than coincidental, but the pattern itself is real, and it is enormous. What drives cosmologists is the question of whether the web continues beyond what we can map. Inside the observable universe, the surveys agree, the filaments and voids repeat on scales up to hundreds of millions of light-years. The Hercules Corona Borealis Great Wall is an outlier, a challenge to assumptions, but the general web-like pattern is consistent with the cosmological models. Beyond the observable horizon, there is no direct evidence either way. The cosmological principle says it continues uniformly. The same physics that built the web inside our observable bubble was operating everywhere in the universe simultaneously. The same fluctuations, the same dark matter, the same gravity. The structure goes on as far as we can see, and the assumption is that beyond our horizon, more of it continues in the same vast pattern. Every object you see in the night sky is showing you its past, not its present. This is not a poetic way of saying something. It is the literal, physical consequence of the speed of light, and it gets stranger the further out you look. Start close. The moon is roughly 1.3 light seconds away, which means when you look at it, you're seeing it as it was a little over a second ago. Barely worth noting. The sun is 8 light minutes away. The image in the sky at any given moment is the sun as it looked 8 minutes before. If the sun vanished right now, you would not know for another 8 minutes. You would stand there warm, looking at a star that no longer existed. Push further out and the numbers change in a way that stops being comfortable. The nearest star system beyond our own, Alpha Centauri, sits 4.2 light-years away. The light reaching your eyes from that direction left during a specific year, one that actually falls within recent human memory. The star you are looking at is a time-delayed broadcast. Now extend that to the nearest galaxy visible to the naked eye. The Andromeda Galaxy is approximately 2.5 million light-years from Earth. The light currently arriving from Andromeda left its source before our species existed in any recognizable form. Homo sapiens had not yet appeared. The creatures walking the planet at that moment were making crude stone tools and had no concept of fire, let alone galaxies. That ancient light crossed 2.5 million years of empty space and landed in your eye tonight. And your eye called it the present. It was not the present. It was a photograph of the past that just arrived. Go further. The Virgo cluster, the massive concentration of galaxies that anchors our corner of the cosmic web, sits roughly 50 million light-years out. The light leaving Virgo right now will reach Earth in 50 million years. The light reaching Earth right now left Virgo 50 million years ago, when the last non-avian dinosaurs had been dead for only a few million years, when early primates were small, tree-dwelling creatures with no particular claim to the future. That cluster of thousands of galaxies, vivid in modern telescope images, is a document of a time so remote it has no connection to human experience at all. And Virgo is not even close to the edge of what telescopes can reach. The most distant galaxies ever imaged by Hubble sent their light toward us more than 13 billion years ago. The universe was less than 1 billion years old. Those objects existed in a cosmos that looked almost nothing like the one we inhabit now. Galaxies were smaller, more chaotic, crashing into each other constantly, still assembling themselves from gas and dust. Some of the specific galaxies in those deep field images almost certainly do not exist anymore in that form. They have since merged with neighbors, transformed, built up central black holes, changed their shapes entirely. The image is not wrong, it is just old. It shows something real that happened in a real place. That place simply does not look like that anymore, and light from its current state has not had time to arrive. This is the part that takes some sitting with. When astronomers produce a map of the observable universe, they are not mapping the universe as it currently is. They are producing a composite document, stitching together observations made across wildly different points in time. Nearby galaxies are shown as they look now, or close to it. Mid-distance galaxies are shown as they looked hundreds of millions of years ago. The most distant objects are shown as they appeared billions of years before Earth formed. All of it is displayed together on the same map, as if it was simultaneous. None of it is simultaneous. There is no universal present tense at cosmic scales. This is not a philosophical claim. It follows directly from Einstein's relativity, which established that simultaneity is not a fixed property of the universe. Two events separated by billions of light years cannot be meaningfully described as happening at the same moment. The concept simply does not apply. When someone asks what is happening in a galaxy 6 billion light years away right now, the question does not have an answer that physics can provide. What we know is what happened there 6 billion years ago. What is happening there at this moment is information that will not arrive for another 6 billion years, long after Earth is gone. What this means for the night sky is something most people never think about. When you stand outside on a clear night and look up, you are not seeing one moment in the universe's life. You are seeing a layered composite of thousands of different moments stacked on top of each other. A nearby star at one layer, a distant globular cluster at another, a smear of the Andromeda galaxy at yet another, and deep field galaxies at the bottom of the stack, representing the universe's infancy. The sky looks still. It looks like a single snapshot. It is actually a collage assembled from light that has been traveling toward you for periods of time that range from minutes to billions of years. Call it a time machine if you want, but that undersells it. A time machine implies you chose to go somewhere. This is not a choice. Every photon that hits your eye carries a specific timestamp from a specific source. You cannot opt out of the time delay. Looking and seeing the past are the same act at cosmic distances, and there is no version of looking that shows you the universe as it actually is at this moment, because that information has not arrived yet and will not arrive in any human lifetime. The further you look, the older the image, and there is no flaw to how old it gets. The cosmic microwave background, the oldest light in the universe, shows us a moment 380,000 years after the Big Bang. That is essentially the opening frame of a very long film. Everything that has happened since is written in the layers above it. The night sky is not a picture of the universe. It is a stack of images taken at different moments across 13 billion years of history. In about 150 billion years, the night sky will be almost perfectly empty. Not dark the way it gets on a moonless night in the countryside, where you still see thousands of stars and the faint smear of the Milky Way overhead. Empty in a way that has no comparison on Earth today. A darkness without structure, a sky without depth. Every galaxy outside our local group, every one of the 2 trillion, will have crossed the cosmological event horizon, carried beyond reach by accelerating expansion. They will not be destroyed. They will not disappear in any dramatic sense. They will simply recede until the space between here and there stretches so fast that no signal, no photon, no information of any kind can ever make the crossing. Gone from us permanently and completely and forever, the local group will still exist. The Milky Way, Andromeda, the Magellanic Clouds, and the roughly 50 smaller galaxies gravitationally bound to this region of space, these will remain. Gravity, at close enough range, is stronger than expansion. The members of the local group are not being pulled apart, they are falling toward each other. Andromeda is already approaching. In about 4.5 billion years, it will collide with the Milky Way in a slow-motion merger that takes hundreds of millions of years to complete. What emerges from that collision will be a single large elliptical galaxy, sometimes called Milkomeda by astronomers who spend their time modeling the future. And over the billions of years that follow, the rest of the local group will be absorbed into it as well. One merged object, surrounded by void. This is what the far future holds for any observer who happens to exist. A single galaxy, one island of stars in an otherwise structureless dark. No visible neighbours, no other light sources on the horizon. Point a telescope outward in any direction and find nothing. Run a survey of the sky, find the same result. The universe from that vantage point would appear static, isolated, eternal in its emptiness. No redshifted light from receding galaxies because there are no observable galaxies left to redshift. No cosmic microwave background detectable at useful signal strength, stretched by then to wavelengths so long that even the most sensitive instruments would lose it in the noise. No expansion rate to measure, because there is nothing left to measure it against. The evidence that built our entire model of cosmology, all of it, gone. Here is what makes that genuinely unsettling. Those future observers would not know any of this. They would have no data pointing toward a Big Bang, no distant galaxies to map, no CMB to study, no Hubble constant to argue about. They would look at their single merged galaxy and conclude, reasonably, based on everything available to them, that this is the universe. One galaxy, stable, surrounded by nothing. They would build theories consistent with that observation. Those theories would be wrong, not slightly wrong, fundamentally, completely wrong about the nature of the cosmos they inhabit, and they would have no way of knowing it. The evidence for the truth would be unreachable, moving away from them at speeds that make retrieval physically impossible. This is not a hypothetical failure of intelligence or method. It is a failure imposed by physics itself. The universe will hide its own history behind an expanding horizon. The chapters that exist right now, the CMB map, the galaxy distribution, the clear observational signal of expansion, those are chapters written in light, and light has a finite speed and a finite age. As the universe grows and accelerates, those pages get carried beyond reach one by one. What we have access to right now in this era is extraordinary by any comparison to what came before or what will come after. 30 billion years ago, The universe was too young, too dense, too hot for the kind of observers capable of doing cosmology. Stars had barely formed. Galaxies were still assembling. The conditions that allow complex chemistry, rocky planets, and long-lived stable systems were not yet in place. And 30 billion years from now, long before the full emptying of the sky is complete, the accelerating expansion will already be erasing evidence, pulling the farthest and most ancient signals beyond the horizon one after another. The window is specific. It is now. Consider what that means in practice. Every observation astronomers have made about the large-scale structure of the universe, every measurement of the CMB, every galaxy survey, every supernova light curve used to trace the expansion history, all of this has been possible only because we exist in a particular moment, early enough that the ancient light is still arriving, late enough that we have the technology to read it. The intersection of those two conditions is narrow. It will not persist. There is something almost uncomfortable about this. The universe has a story, and right now that story is fully visible. The beginning is still detectable. The structure that formed afterward is still mapped across the sky in the distribution of galaxies. The rate of expansion, the composition of the cosmos, the geometry of space, these are measurable today in ways they will never again be measurable from any vantage point inside this universe. The information exists. It is available. Some of it is being collected, and some of it is still arriving, and none of it will be available to whatever comes after us by a long enough margin of time. Future observers who somehow reconstruct the truth would have to do it theoretically, through inference and mathematics, with no observational anchor at all. They would have to deduce that there was once a Big Bang, that there were once 2 trillion galaxies, that space itself was once measurably expanding, and do all of that with no direct evidence remaining. That is not cosmology. That is archaeology without artifacts. The universe is already enormous beyond anything that fits cleanly into human intuition, and it is growing. And as it grows, the fraction of it we can see is shrinking. The observable universe is not a fixed thing. It is a moment. This moment. Every era of cosmic history has had its own version of the observable universe. Ours happens to be the one with the most to see. Pull back from all of it and try to hold it in one thought. The observable universe is 93 billion light years across, not 13.8 billion. Not the number that gets printed in textbooks and repeated until it feels true. 93 billion light years, and that is only the part from which light has had time to reach us. Beyond that boundary, the universe almost certainly continues. Same galaxies, same stars, same physics, just more of it, extending past anything we can see or measure or meaningfully imagine. 2 trillion galaxies inside that bubble alone, each one containing hundreds of billions of stars. Most of those stars with planets. The numbers stopped being useful long before you got to this point in the video. At a certain scale, figures like these are not really quantities anymore. They are a single impression, a weight pressing in from every direction at once. The universe is not large the way a continent is large, or the way an ocean is large. It is large in a way that has no earthly comparison and no useful analogy. It is large in every direction simultaneously, at every level of scale, with no confirmed edge and no confirmed center. Go outside on a clear night. Get away from the city lights if you can. Look up at the Milky Way stretched overhead, that pale river of light crossing the sky. Every point in that band is a star, most of them older than our sun, many of them with planets orbiting in the dark. The galaxy itself runs 100,000 light years from end to end. That is just our galaxy, one of 2 trillion, beyond the Milky Way, beyond the local group, beyond the Virgo supercluster and the filaments of the cosmic web. There is space that no telescope has ever seen and no instrument we currently possess can reach. That space does not care about our instruments. It continues anyway. And beyond even that, depending on which physics you trust and which mathematics you follow, there may be other universes entirely. Other bubbles where the constants of nature are different, where the story of reality began differently and went somewhere else. The measurements say the universe is geometrically flat. A flat universe can be infinite. If it is infinite, then everything that can happen does happen somewhere, an infinite number of times. That is not poetry. That is what infinite means. Stand under the Milky Way and try to hold all of it at once. The 93 billion light years, the 2 trillion galaxies, the space beyond the horizon, the inflation that made the observable universe a rounding error inside the total. The universe keeps going and nobody knows when it stops. Some of the best evidence we have suggests it doesn't.